today is Matthew Kahle, and he's going to be giving us a talk on topology of random complexes.
All right. Thanks very much for the invitation to speak and for your interest. So I think today's talk will be sort of a survey of what I think of as an emerging area, sort of probabilistic topology. The goal is to construct random spaces and then to sort of compute their topological invariance. And there's various reasons to play this game, and maybe I'll try to indicate some of the motivations as we go along. Since it is a survey, I think I'll try to introduce several different kinds of random complexes today and talk about what we know and don't know about them, indicate a lot of open problems along the way. So first, I'll mention maybe the mother of all random simplicial complexes, the Erdos-Renyi random graph, G and P. It's a random graph. It has n vertices, and each of the n choose 2 possible edges appears with probability p, and that those are independent choices. So it's just, if you set p equal to 1/2, you would think flipping a coin for each of the n choose 2 edges and include it if it's heads and don't include it if it's tails. Okay. So it's a little bit too restrictive to make p constant, or just to look at a particular n and p. Might not be interested. It might not be mathematically interesting. So frequently we let p be a function of n, and the number of vertices goes to infinity. And the sort of remarkable discovery of Erdos-Renyi was that if you ask about many different properties that a graph might have, and then if you set some function, p to be p over n, and let n go to infinity and say, what is the probability that you have that property? Very often the probability is either 0 or 1. There's actually sort of theorems that quantify that, but let me just give you, and that the threshold between can be very, very fast. So one example would be the property contains K4 subgraph. K4 is the complete graph on 4 nodes. So our claim is going to be that if p is large enough that you have lots of these, and if p is much smaller, then you don't have any. So this property has threshold, something like p equals n to the minus 2/3. So why? Well, one way to look at it would be to count them. The expected number of K4, not subgroups, subgraphs, by linearity of expectation, there's n choose 4 possible K4 subgraphs, and then given one of those, what's the probability that it appears, given a choice of 4 nodes? Well, 1, 2, 3, 4, 5, 6 edges would have to appear, and they're independent. So that's n choose 4 p to the 6th. So that's something like 1/24 the 4th p to the 6th. So did I write the wrong number here? I probably want 3/2, right? Oh, sorry. So maybe I did have the right thing. Okay. Is this right? What's on the board?
So you're wondering about what happens asymptotically.
Mm-hmm.
This is an expected number, and
That's
the same as probability of occurrence.
That's good, thank you. So, okay, so it does tell you something if the expected number is 0. Then the probability of any appearing is also 0, or going to 0 as n goes to infinity. So if p equals, say, little o, n to the minus 2/3, or in other words, if n to the fourth p to the 6 is going to 0, the expected number is going to 0. And so then probability that there exist any such subgraphs goes to 0. But you have to, it's a little bit more subtle the other way. Suppose n to the fourth p to the 6 goes to infinity. The expected number of k4 subgraphs is going to infinity. That is actually not enough to tell you that you have any, right? It's possible that you have some funny random variable that just every once in a while is very huge, and the rest of the time is 0. So that, 1 out of a million graphs, you get 1 trillion k4 subgraphs, and the rest of the time you don't get any. But so that doesn't happen. We need a little more information here about distribution of this random variable. The random variable I'm talking about is number of k4 subgraphs. So it turns out we don't need much more about the distribution. Just the second moment would be enough. And the second moment is very easy to compute by hand for a random variable like this, because it's the sum of n choose 4 indicator random variables. I mean, the sort of mantra is, of course, the central limit theorem says that if you sum up a bunch of independent random variables that all have the same distribution, you're going to converge to a normal distribution. But that seems to hold even if not everything is exactly independent. And so most pairs of k4s don't overlap once you have n nodes and n is really large. So you can make very precise statements. So one would be if the expected number of k4 subgraphs was approaching a constant, then we can actually say what the limiting distribution is, and it's a Poisson distribution. And if it's the expected number of k4 subgraphs is like tending to infinity, at least if it's tending to infinity fast enough, then if you renormalize your random variable, then you'll get a normal distribution. But that's a lot more information than we need to just produce one. To say there's at least one subgraph, just the second moment is enough.
How do you get the second one?
Second moment, you just write this random variable, the number of k4 subgraphs. It's a sum of n choose 4 indicator random variables. 0 if that k4 is on, and 0 if it's off, 1 if it's on. And then you just say, ex squared minus ex squared. You can actually just compute it very directly. Every one of those indicator random variables is the same variable. So the only thing that you have to get into is the sort of cross terms where 2 of those overlap. But it's just pure, it's a paragraph of combinatorics that in the interest of time I'm not going to do on the board. But it's a very straightforward computation. Okay, so let's give a slightly more interesting example, although I think this is good to keep in mind as we go through examples, higher dimensional versions of this. So this is actually a theorem due to Erdos-Renyi. If p is much bigger than log n over n, then g and p is asymptotically almost surely connected. And if p is much smaller than log n over n, asymptotically almost surely disconnected. So that abbreviation means just the probability goes to 1 as n goes to infinity.
How does your notation, how does your notation much bigger and much smaller compare
Right.
with what one reads in books?
So I might mean different things at different times in my talk by using this. I really want to be able to just say much bigger, much smaller. But let me give you a more precise statement. If P equals log n plus C over n, where C is constant, then probability G and P connected approaches a constant between 0 and 1, and that constant is e to the minus C. And I think I'll just, because this is a topological statement, I think, talking about connectivity of a space. Well, actually, I want to briefly sketch the proof of this, because this idea of this proof has been useful in other contexts. So, well, maybe I'll just leave that out there. Okay, so idea of proof. So first say P is about log n over n, and ask, are there any any components of order 2? A connected component of order 2. So that would be an edge. So these two are connected to each other, and then they're disconnected from the rest of the graph. Well, so let's look at the expected number of such components. The first thing that has to happen is that that edge has to be turned on. That happens with probability P. And then all the edges connecting that to the rest of the graph have to be turned off. So that's 1 minus P, 2, n minus 2. And since we're just computing expectation, we'll just multiply that by the possible number of pairs of vertices that could be that component of order 2. So remember, linearity of expectation does not depend on independence of events. Expectation is always linear with terms of summing variables and multiplying by a scalar, because it's just a sum or an integral for a continuous random variable. OK, so we can compute this. So this is certainly less than n squared p e to the minus p 2 n minus 2 by using the fact that 1 minus p is less than e to the minus p. And if I write in, I guess this is still equal, or approximately. Nope, that's still, I'll just fill in for p. So n minus 2 over n is about 1. So this is going to be like 1 over n squared to cancel that out. And we'll have something like about log n over n. So we shouldn't expect any components of order 2. In fact, we shouldn't expect any components of order 3 either. And rather, it'll take us a long time to rule out everything if we keep going that way. So we'll write a sum. We'll try to sum up the possible components of order r all the way up to half the size of the graph. So there's n choose r possible sets of r vertices that could be a component of order r. So if it's a connected component, in particular, there's a spanning tree in there that was all turned on. And it's well known to combinatorialists that there's r to the r minus 2 spanning trees on r vertices. So we're going to grossly overestimate the number of components on order 3 to half the size of the graph. So r to the r minus 2, p to the r minus 1, 1 minus p to the r, and minus r. And this is the sort of calculation that's best left to the privacy of your own home. So I'll just sort of just say that you just want to show this goes to 0.
What is this computing?
This is computing. This is expected number of components of order R.
As you said, remember this tree, and remember the beginning that it means something else.
We're overestimating it
Why are we overestimating?
because that's convenient. Because it's too hard to compute the actual number of components.
Why is this an overestimate?
What is an overestimate?
Why is this an overestimate?
Oh, because maybe if there's a component that looks like that, I've counted it like 4 times because there's that spanning tree, that spanning tree,
Okay, so you're replacing each component
by a spanning tree. So that's where that r to the r minus 2 comes. So this is actually a little more complicated expression than with 2. The spirit is the same, but the spanning trees trick is kind of nice. And it's messy and it's not pleasant enough that I want to write it up on the blackboard for you, but you're just going to again overestimate this. Again, we'll use 1 minus p is less than e to the minus p. You'll write this, overestimate that by n to the r over r factorial, and then use Stirling's formula to approximate r factorial, and go on. And 5 or 10 sort of very painful lines later, you see that this thing is going to 0. So we're not done yet. Conclusion, there exists a giant component, at most 1. It's unique, though we don't actually need that fact here. And isolated vertices. That's what we didn't count. So we've ruled out components from order 2 to half the size of the graph. There can't be more than 2 components bigger than half the size of the graph. So there's a unique giant component. But then we've got some components of order 1. And now set p equal log n plus c over n, and say what's the expected number of isolated vertices. And by the way, this isn't just useful inequality. It's not just that 1 minus p is less than e minus p. It's that these are good estimates for each other when p is very close to 0. So if you estimate, well, the expected number of isolated vertices is n 1 minus p to the n minus 1. And that approaches e to the minus c as n approaches infinity. So if you let c slowly tend to infinity, as slowly as you'd like, say log n, which is known to tend to infinity but has never been observed doing so, then that makes the probability that there are any isolated vertices go to 0. But it's actually even better than that. Because we have this structure theorem, and in this regime of P, we know that there's a giant component in isolated vertices. This actually gives us this better statement with just a little more work. What you can actually show is this random variable, the number of isolated vertices. This approaches a Poisson distribution. And there's various tricks to do this. Noga Alan has some beautiful writing about it in his book on the probabilistic method. And there's Stein's method and other ways to do this. So it's not too hard to show that this approaches a Poisson distribution with mean e to the minus c. And then that gives you that the probability that this equals 0 is going to e to the minus c. So that's where this weird exponent comes from. The nested exponent is coming from the Poisson distribution on the number of isolated vertices.
So no, if your sum, if you were foolish and ran the sum from r equals 1 to n over 2, then it failed miserably?
Well, yeah, you won't be able to show this goes to 0. I mean, or you have to be careful about what p is. I was being a little bit vague here and just saying p is in the ballpark of log n over n for going from 2 to n over 2. And if you want to be really precise, I think you need to be at least half log n over n or something. But then for the isolated vertices, if you're really close to log n over n, you're going to get a constant number of them. So you better not be able to show that you're getting 0, because you're getting a positive constant.
So is it true that what actually happens at the margin is you have one big component plus isolated vertices?
And that makes sense. The heuristic is, something like this. Once there's a giant component, let's say there's some other reasonably large size component, then there's a lot of possible edges between them. And so in that way, the giant component gobbles up the second largest component and all that very quickly. And then the last thing that happens, you can actually see it carefully. You can see it in the evolution of the random graph. You could see it at the end, gobble up components of order 3, then 2, then 1. What's probably the most interesting part, though, is the emergence of the giant component itself, which is for sort of much smaller p than this. Instead of log n over n, it's when p equals 1 over n. And that's where the giant component emerges. So you can say things like if p equals 1.01 over n, then with high probability, there's a component that can a positive fraction of the vertices. And if you're 0.99 over n, then all the components have order log n. But you can get much more precise than that.
Wait, is 1 over n? So you have n over 2 edges?
That's right. So it's actually sort of remarkable study that they found that so the giant emerges when p equals 1 over n. And what's not trivial, but it's relatively straightforward to prove, you can do it in a day in a graduate probability course or something, is that if you're 0.99 over n, that you only have components of order log n, and at 1.01 n, there's a unique giant component, and it contains a positive fraction of the vertices. So what happened? So they kind of took their microscope and looked closer at that, and the right thing to look at is not moving a constant there, but something like 1 over n plus c n to the minus 4/3. And now you move that c around, and you can see, actually if you set it equal to exactly 1 over n, you get the giant component of order like n to the 1/3 or something. There is some intermediate state. And if you allow this c to continuously vary, you can see the how that giant emerges. There's a 200-page paper by Don Knuth and co-authors called Birth of the Giant, examining it in exhausting detail. You actually don't know from the title of the paper whether the title of the paper is about the giant component in the random graph or about the paper itself, because it's 200 pages long. But anyway, this is very well studied.
What varies in the graph as c changes in this last one?
I can't remember what the statement is. So think of c as constant. And if you make c like minus 10, then you'll get the components are all still somewhat small. And if you make c 10, then they're all somewhat large or something like that. So this is, I want to mention this because now I want to talk about higher dimensional analogs of Erdos-Renyi random graphs and also more geometrically defined things as well. But what we'll talk about is thresholds for vanishing of homology, and we'll also talk about expectations of the Betty numbers. But what I feel like is missing from this picture is this whole story of the giant component that's known so well about the random graph, and in many different guises. So in percolation theory, for example, that's a very different kind of random graph, but you could also say is a one-dimensional random simplicial complex. Include each edge on the lattice, the square lattice in the plane, with probability p independently. If p is less than 1/2, you have only finite components with probability 1. And if p is greater than 1/2, then with probability 1, you have a unique infinite component. So that sort of is not exactly, it's something about connecting, but it's not really something that you'll measure with just homology. It's not something about Betty numbers. It's not something about the homology class vanishing or not. It's about the size of the class. So that's something to kind of keep in the back of your mind as I'm talking about these other things. Is so far we've just found things that are more analogous to these kinds of statements, thresholds for vanishing of homology, but we don't really have analogs of this sort of statement, and it would be really quite nice to have that. Okay, so Lenil and Meshulam, as far as I know, were the first to define a higher dimensional analog of the Erdos-Renyi random graph. Lenil and Meshulam said Y and P is a random simplicial complex, and it has n vertices, n choose 2 edges, so all possible edges between those vertices. You start with a complete graph, and then the randomness is for the 2-dimensional part. Each of the n choose 3 possible 2 faces is included with probability p independently. And they gave a beautiful sort of homological analog of this. So this is Lenil and Meshulam's theorem. If p is much greater than 2 log n over n, then h1 y with z mod 2 is 0 asymptotically almost surely. And that's the content of their theorem. If p is much less than 2 log n over n, then it's pretty easy to show that it's not 0. I guess I should say this is true of the Erdos-Renyi random graph too, that it's easy to show it's disconnected when it is, because all you have to do is give one isolated vertex. Find one of those. To get that it's connected, you have to do more than just rule out isolated vertices. We had to first give that structure theorem that we're only down to a giant component in isolated vertices. So all their work is here. And I'm not going to say much about their proof other than this is true, what's written, but if you look at their paper, they're really talking about H upper 1. It's a cohomological argument. And you can almost see, I mean, for those of you who know sort of the difference between homology and cohomology, you can almost see the cohomology lurking here, and that we have these, what we're trying to rule out, these connected components, and that has something to do with these bipartite subgraphs that would connect your graph to the rest of the graph. And once your component is large enough, you would really expect that at least one edge of that bipartite subgraph would be there. But this is a complete bipartite subgraph, but that complete bipartite subgraph is a cocycle. If you take this set of vertices, say z2 coefficients, just think of that set of vertices, and then look at the image under the co-boundary map, you're going to get a complete bipartite graph like that. So this theorem is a sort of a perfect cohomological analog of the Erdos-Renyi theorem. And their method is it's something like this, although the combinatorics is a lot more hairy, and it's not easy at all. And they have to introduce a new tool to sort of say what they're doing with counting cocycles and something like that. Yeah?
Like they're making this random complex by first sticking in all of the edges and then putting in some triangles. Did the story change much? I mean, another naive thing, you might just pick a bunch of triangles and then put in the edges for those.
Right. So that does also seem like a natural complex. Maybe you could think of that as the pure dimensional version of this. So at a certain point, though, these two models will coincide, because and that point is when every edge is covered.
So, for example, in the original Erdos-Renyi thing, some of the person was saying, instead of throwing in all the points, you just throw in edges.
That's right.
And presumably, I assume you get the same statistics.
More or less, although things are, I think it's a little bit subtle. So you can see in the Erdos-Renyi case, once what we cared about was this threshold for every vertex has gotten at least one edge. We had to rule out isolated vertices. Once you're past that threshold, these two models coincide, right? Because then now all the vertices are there. So same thing here. Once we're past this threshold, so this, I think in either case, this is going to tell you once you have enough triangles, say with the model you suggested, you will still kill H1, but something else happens before that. Before that, these two models are different. The one you suggested is pure dimensional, and this one isn't.
Well,
So
certainly on a technical level, I think from a very cursory acquaintance with the paper is the way you prove that H1 is not 0 is you find some uncovered edge.
that's right.
And here there are no uncovered, so you have to work harder.
That's right. That's a good point. I mean, even the question of when does that model with the triangles, just Theorem and random triangles, become connected might be, I mean, that's a question that wasn't there with this model that you'd have to think about it.
So you're saying for them an uncovered edge is sort of like the point component.
That's right. Thanks, Bob. That's what I didn't say was here. That's why this direction is easy. Much easier is they just have to show one edge. And if p is much less than 2 log n over n, like say if you're 1.99 log n over n, you almost certainly have uncovered edges.
Are there any guesses that anyone's thought about for the generalizing the giant component for this case, or that no one's got any real?
I think there are some guesses, and I've even got some guesses myself, but I feel like I'm not ready to talk about them in this talk. So please forgive me for not answering that question. But I think as far the rumors I've heard is that Nati Lanil is also doing some computer experiments with these, and I'd really like to hear about the results of those. So with this same model, Eric Babson and Chris Hoffman and I looked at pi1. Sorry for briefly repeating the content of my 15-minute talk from last week for those of you who were there. But if p is much less than n to minus 1/2, then pi1 is not 0. And if p is much greater than n minus 1/2, pi1 is 0. So the threshold for the fundamental group is a lot different than the threshold for first homology. So here, by the way, see, I try to suppress notation, and then I feel guilty about it and feel like I have to say what I really meant. So we have to push off the boundary a little bit. So we know we've got the right exponent, but unlike the Lanil-Meshulam, there's got the log term and they've got the right constant in front, we have no idea about that. We just know we got the right exponent. So, and this required a lot of work, and it ends up being sort of a geometric group theory argument following ideas of Gromov and local to global for isoperimetry. But since it's a survey talk, I don't want to talk about this too much. I just want to sort of, and since I talked about this last week here, so here's some questions though. If p is between log n over n and n to the minus 1/2, every cycle is a boundary, but not of a disk. So what's it a boundary of? I mean, you can imagine, you take some cycle on the graph and it's bounding something according to Lanil-Meshulam. So maybe it's some multi-hold manifold or something. But we know it's certainly not a disk. So that would be quite interesting to know what are these things bounding. Estimate the genus. There's various ways we could quantify this.
What did you write them there? But not what?
But not, it's the boundary, but not of a disk, not of an immersed topological disk. Sorry, my handwriting got a little bit wild there. Also, another question in this area that's particularly appealing, I think, for a lot of reasons. What's the threshold for H1, for vanishing of H1 with z coefficients? So this was extended by Meshulam and Wallach for arbitrary finite field coefficients, and they all have that same threshold, 2 log n over n. But that doesn't rule out the possibility if p is like n to the minus 0.99 or something, that you still have integer homology for, but that it's growing within. as n's going to infinity, that you have p torsion, that p can't be big O of 1, but you could have p torsion where p is tending to infinity.
Yeah. I know you don't talk much about this linear Michelin proof, but how are you using the fact that the coefficients are
It comes in an essential way in that they have to count the total number of co-cycles. And so then to count all the co-cycles, they need to not just count the sort of complex, they're counting all of them really, not just the subcomplexes that could support it. So then they have to multiply by the size of that possible subcomplex with the coefficients to that power of the number of faces or something. So that doesn't work at all if you have z coefficients. So that something that's finite and that they're trying to control the size of as a function of n and p becomes infinite as soon as you put an integer here. So this will be interesting no matter what it seems like whatever the answer is. I think most people, and probably me, would tend to guess that the threshold for integer homology is the same as finite field homology, but we definitely need new tools to attack it. And as you'll see, as I mentioned in the remaining time, a couple other kinds of random simplicial complex, it's the same situation in that we can find thresholds for vanishing of homology, and we can estimate Betty numbers, and sometimes say a lot about the Betty numbers. But we can't, so far, none of the tools. What was that?
Make it more vanishing, higher dimensional?
Let's see. So can you elaborate the question? I'm not sure if I understand what you're asking.
So find out that h1 is 0 in the case of n greater than n1/2. So that, about h2? Do you have any conditions that would imply that h2 is 0? You said that already.
That's right.
They are all boundaries, but
that's right. So there is actually, Kozloff wrote about this. It's easier than the Lineal-Mechoulam threshold. So here we've got this two-dimensional random simplicial complex. There's only two interesting homology groups, H1 and H2. And if P equals omega over n, where omega tends to infinity, then H2 of y and p, and here it doesn't matter what the coefficients are with any coefficients. The coefficients don't come into play really in Kozloff's argument. How does this go? Not 0. And if p equals little o of 1 over n, then h2 equals 0. So now the threshold's going the other way. But notice that it's not the same place, this threshold that the Lineal-Mechoulam place happens. So if p is like log n over n, or anything really between 1 over n and log n over n, then you get both h1 and h2 non-vanishing. There's a very small interval where that happens.
And I guess another thing, you can ask both about even the Erdos-Renyi case. So in the Erdos-Renyi cases, you can try and compute the fixed p. You want to compute the expectation of the number of connect components. So similarly here, you can compute the expectation of the rank of your favorite group.
That's right.
Has it been done? Really?
I don't know if it's been done for this Lineal-Mechoulam model.
And for the Erdos-Renyi, presumably it has been.
But well, I'm not sure if it's been done for all for all possible ranges of p. That a lot of theorems that people write down for Erdos-Renyi graph need some hypothesis on p. So here, if we say p is in the ballpark of log n over n, then I just told you the answer before. It's a giant component in isolated vertices, and the number of isolated vertices is going to a Poisson distribution. And so there, Betty naught is 1 plus this Poisson distribution. Or reduced homology is exactly that Poisson distribution. So there we can say quite precisely, but like say p equals 1 over n, in that regime, I think it'd be interesting to know what's the size of the Betty numbers. And I'm sure you could read it out of Bolabosh's book. You could, in some sense, yeah, they've talked about the number of components. But I think it's hard to because of the structure changes in the graph, I think it's hard to write down one theorem for sort of all range of p. You'd say, well, for sufficiently large p, it's 0, reduced homology. For p in this intermediate range, log n plus c over n, it's Poisson distributed. And then for slightly smaller p, you'd need some other, you'd say it's probably growing like a power of n.
But I guess also the previous question about the rank of H2 can be interpreted as you just take the model one level up, so you just have a complete hypergraph, right, or whatever. You have all the triangles,
Mm-hmm.
and now you're throwing in balls,
Mm-hmm.
fill them in, and then you can ask the same
Mm-hmm.
kind of question. Presumably people have that.
It seems like a very natural question. I'm just not aware of anybody writing anything down about it so far. So
Can you make a guess as, I mean, the threshold of H1, I would think you could do a computer simulation and decide what's probably true. Has somebody tried to do enormous computer simulation?
I think so, but here's something that's quite funny, is that they also tried to do that for pi1 when we were trying to prove it.
Much harder on it,
Okay.
as far as the computer's concerned.
I think so, but in fact, but it'll also answer the other question. The computers seem to say, I don't know how big their simulations were. I wasn't the one doing it, but say 100 vertices, and they're adding the faces, and then they could say, oh, pi1's 0. They found some sufficient condition for the group to vanish. Everything canceled. That actually happened here when homology vanished. So for a little while, I was trying to prove that their threshold was the same for pi. That was the threshold for pi, and I only had this at first as an upper bound, and then we did a whole lot of work and figured out that it was the right answer. So, so the computer simulations actually showed pi1 vanishing. So then H1 was the coefficients would also be vanishing. So, but then I've heard that maybe they're continuing to do more computer simulations that maybe are more refined or bigger complexes. There's got to be something happening there that they can tell.
Is there a way that they're shrinking to 0? I mean, that's but in terms of the n, p greater or less than, that the groups are going to be shrinking.
Mm-hmm.
And the question, say for instance,
There's a lot that we don't know about these groups.
How about the finiteness as a stat
That's right.
of the groups?
So we know if p is this small that it's not just non-zero, it's an infinite group. It's hyperbolic. But we don't know anything about its abelianization. So, okay, so let me tell you about a very different model that I studied in my PhD thesis.
You assume the hypothesis that you have this regular type of simplicial complexes. Is that what you were doing for all these results, or
So far, I'm just talking about lineal Meshulam 2 complexes. And so now I want to tell you about something very different, which is
the clique?
random clique complex. Take the clique complex, I'll tell you what that means in a second, of the Erdos-Renyi random graph. So this is a different higher dimensional generalization of the Erdos-Renyi random graph. So clique complex means fill in all possible simplices. So whenever you see 3 cycle, fill it in with a triangular 2 cell. Whenever you see complete graph on 4 vertices, fill it in with a solid tetrahedron, and so on. So it's the maximal simplicial complex compatible with that graph. So now the problem, and this isn't just a passing remark, this is essential to this kind of model and to other kinds of models. Now homology is essentially non-monotone. It's not just that it might be non-monotone. So in other words, when I'm adding edges, I'm adding lots of higher dimensional faces, so I'm adding generators and relations. And who knows what happens to homology. It could be something like this, where I add an edge and that kills homology. Where if that had been on a 6 cycle, then I add that edge, it increases homology. So So let me give you a picture of what actually happens with the Erdos-Renyi random complex. Here, I'll save one for myself. So this complicates everything because we're used to studying random graph properties that are monotone, such as connectivity or contains K4 subgraphs or something. So now it's not even clear what you want to try to prove, that you could prove anything. So I'll give you some examples of theorems, though. So this is work from my thesis. If P is if P is small enough or P is large enough, then kth homology vanishes. And there is an intermediate range where it's non-vanishing. So monotonicity now is going to be replaced by unimodality or something. And that's what you sort of see in these pictures. By the way, these beautiful pictures are due to Afra-Zomerodian. So this is what you see here. That top picture is 100 vertices. And he just added random edges one at a time. So by the time you get to the right side of the bar, that's 3,000 edges that he's added, I think, right? So 100 choose 2 is like 5,000. And then times 0.6 is he's added about 3,000 random edges, and he's computed all the way up to fifth homology group. And then the computations are getting wild. You only have 3,000 edges, but you have millions of higher dimensional faces. So even though it's 100 vertices. But so I should say, by the way, that these theorems preceded this picture by a couple years or something. So I was sort of hacking this out, trying to figure out what was going on while I was working on my thesis. And then later Afra showed me these pictures that were very consistent with what I had eventually sort of the image I had in my head. But I was so surprised to see these curves as smooth as they were and well-defined on only 100 vertices. I was delighted, actually, to see these pictures. So,
Videos of these simplicial complexes forming.
what was that?
Are there videos?
I would love that. I'm not sure how we draw them, but so we can actually say a lot more than the HK is non-zero here. You could say the expectation of the Betty number is approximately, this is all for the clique complex now. So let's see, k-dimensional face comes from a k+1 clique. So this should be some constant n to the k+1, p to the k+1, choose 2. So actually, what this number is, it shouldn't be mysterious. This is the same as the expected number of k-dimensional faces asymptotically. So it's as large as it could be, kth homology. But this only works for, if you notice the p that we can show this for, it only works for 1k at a time. And you look at this picture, and it almost makes you wonder if that's what's really happening, that Betty 1 comes in and goes out. And right as it's going out, Betty 2 comes in, and then Betty 3 comes in. So I've almost proved that, but these don't match. So my conjecture would be that this theorem can be improved to if p is greater than -1 over k+1. I gave some evidence of that. If p is much less than n to the -1 over k, or p is much greater than n to the -1 over k+1, actually, Bob, a random Morse function shows you that homology is small. Shows that the expectations, say, compared to the number of k-dimensional faces at least, goes to 0, where if you're in between those two thresholds, the expectation goes to 1.
So this graph seems to indicate also that with probability 1,
that's a good guess. I mean, that's what I think is probably going on. But let me rephrase this a different way, because I think it might make it enticing for some people to think about with me this year. I hope it does. So if you set p, the right to be the right function, you can make the dimension of these complexes whatever you want. So we already saw the threshold for K4 subgraph, so that's the threshold for a three-dimensional clique complex, right? So set p equal to whatever it is to make a random d-dimensional clique complex. Then instead of phrasing everything in terms of n and p, I'll phrase it in terms of d. What we know is hk equals 0 when k is less than or equal to d over 4, and when k is greater than floor d over 2, it's not only non-zero but huge when k equals d over 2. So we've showed that 3/4 of the homology groups are vanishing, and that there's one non-vanishing, but my guess is that it's probably just one that's non-vanishing. I've also showed that there's one that accounts for almost all of the Euler characteristic. There's one that's much larger than the rest. But there's still something to do here to show that hk, to get, make that d over 2, less than d over 2. So by the way, similar remarks here hold about torsion, and here, whether what I'm saying is true or not about there's really only one non-trivial dimension of homology, it is true that most of the homology is here, and it would be interesting to look at that with z, that homology group with z coefficients, and try to understand its torsion.
If it becomes d-dimensional, what's the chance that it's going to be a d-manifold?
Almost 0. I mean, it's going to 0 very quickly. The only random simplicial complex that's manifold that I know of was studied by Pippinger and Schleich, and what they did was they glued triangles together randomly along edges. And you can do that for higher dimensional, for d-dimensional manifolds, but you don't get a surface, you don't get a manifold anymore. You do get a pseudo-manifold that way. But I think it would be quite interesting to know how, take a random d-dimensional manifold, or to even fix the manifold and take a random triangulated sphere. So one way to do it that's actually well studied is to take a random polytope, but what we know is that almost all simplicial spheres are not boundaries of polytopes in higher dimensions. So if we could really find a random triangulation of a d-dimensional sphere other than with this convex geometry, that would be quite interesting. It would let us test the G conjecture. So Stanley proved, he characterized F vectors, for example, of simplicial polytopes, but there's no theory like that for some just simplicial complexes that are homeomorphic to spheres. There's a lot of reasons why I think it would be interesting to, I guess actually there's one work on random manifolds that I know about, and that's Thurston taking like a random cover of a fixed 3 manifold. So fix your base manifold and now take random covers of it, I guess by taking random subgroups of your fundamental group or something. So I think it's closely related to Gromov's stuff on random groups, but a more geometric or more topological point of view. So then maybe in the last few minutes, let me tell you about what's been happening lately, which is the geometric version of these. And it's also in this same kind of paradigm where things are not monotone anymore. So take n points independently and identically distributed in RD according to some distribution. Think a Gaussian, or think uniform on a smoothly bounded convex body. Connect by edge if the distance between them is less than r. But r is going to be a function of n, just like before. And n will go to infinity. And now we have a graph, and so we could build the clique complex again. You could study homology of this. And
about the same as Viator's rips.
Yeah, so the clique complex here is also called the Vietoris-Rips complex. Thank you. And that's actually the other thing that's illustrated in your handout. So the first one was 100 points Erdos-Renyi random clique complex. This is a random Vietoris-Rips complex on 100 points in the 6-dimensional cube. Again, computation due to AFRA. And notice, by the way, that the pictures are the same size, but the scale, the vertical axis is much smaller, that you hardly get any homology here. But what I really love about it is that instead of what looks like a forced oscillator, it looks like a damped oscillator now, the Euler characteristics say, if you just wanted to graph one number. And there's, I have a paper, couple papers on the archive about these sorts of things, and we get similar statements. Now, actually, in this case, I know that there's an interval in which homology is non-vanishing, and outside that interval, it's vanishing. So there's not this kind of little bit of a gap like the Erdos-Renyi case. And joint work with Elizabeth Meckes, we looked through this kind of complex and this kind of complex and proved central limit theorems for in the regime where we know that the Betty number is non-zero. We could show actually what its limiting distribution is. So if you renormalize it so that it's mean 0 and then that its variance is 1, that it's actually approaching a Gaussian. Or if it was in the range where it's actually constant in expectation, it approaches a Poisson distribution. So now we're starting to know some things about the limiting distributions of these Betty numbers. And this might be these sort of geometric random complexes, I think. I'm sorry I didn't have more time to talk about them, but I think these are maybe things that are more of interest to people in statistical mechanics or in mathematical physics. So that you can imagine other sort of geometrically motivated random simplicial complexes, one that it seems very appealing and doesn't seem to have been studied much so far, for example, would be the analog of percolation theory to higher dimensions. So take the lattice, the cubic lattice in R3, and insert square plaquette faces independently with probability p, and now ask questions about thresholds for h1 or pi1 of cycles of that, and see if there's any analogs of kind of classical percolation in the plane. Let's see. I feel like I had some more questions I wanted to leave you with, but I'm out of time, so I'll end there. Thanks.